Okay. So, we are going to now calculations, diagrammatic field theory. So, these are Feynman diagrams and we will calculate for phi 4 theory the one. So, Klein Gordon I am going to put perturbation which is phi to the power 4. So, we had phi squared, but we will put phi 4, but before we go to that we need to get some more theorems. Okay. So, there are a lot of theorems and the one which I am going to discuss today in 15 minutes is Wicks theorem, same weak rotation. Okay. So, if you have, if system is in equilibrium, then we have m point correlation. Okay. Make m even. So, x1 x2, so that so these are fields or some variables at m points. Now, we can break it up into products of 2 point correlation. This is a 2 point correlation, no. So, in fact, these property of Gaussian variables with variables with the probability distribution which is exponential, this type thing. So, all these variables satisfy this property. To give an example, let us say I have random variable with 0 mean, mean is 0. Okay. So, let us keep that for simplicity 0 mean, and I want to compute x, y, z, w. All of them are following Gaussian random probability distribution. This can be written as sum of products of 2 point correlation. This you know already. Okay. If you done probability theory course, this is a standard thing for in probability theory is written as x, y, z, w. This one, what else? X, z, y, w, then x, w, y, z. There are 3 possibilities. Okay. There is only 3 possibilities. And these are classical. No, I am not doing this. I mean, they are not operators which can commutation. I am not worrying about. So, that is why statistical field theory is a good point to discuss, and quantum is more complicated. We will postpone it for future. Now, this for 4, but we can also do it for 8. Okay. So, but you just have to write down all possible combinations. These are even number of variables, odd number of variables, x, y, z, what happens? 0. All odds are zeros. Okay. So, there is a property of this kind of random variables, and how to prove it? In fact, this is called Wicks theorem. Okay. And which is used heavily in field theory. Statistical field theory, we just need them as the classical variables. But in quantum field theory, these are operators x, y, z, w. So, we need to treat them as the time ordered products, and then it is more complicated. Okay. So, I will prove it for classical, okay, and I am going to state the result for quantum. I need to state it. This is a field theory course, but it has complicated aspects. A proof is nice. Okay. I again saw the proof. There is a book by Kopitz. This is a nice book. Okay. So, I will tell you the title, but this is a book where I took this derivation from. Statistical field theory. Okay. So, we had this formula before, right. So, we have source term here, and we wrote like that. We need the source term. For correlation, source term is required, because I am going to take derivatives and pull out x, standard thing. Okay. If you do not remember much in the course, at least you should remember that part. Okay. Now, we put a n normalization which is inverse of this. I basically take it to the left. Okay. Of course, I need to invert it and just to the left like that, and this we call it ZB, partition function normalized, or is a symmetric matrix, and we wrote that this is a density matrix, and so any function fx I can compute using density matrix. Okay. And this is a side remark, but Now let us get to Wicks theorem. So, I have this B transpose X, right, B transpose X. So, it is B I X I. I just expand the exponential as this, all right. So, we just expand it. So, now I am looking at this ZB, which is a expectation value of e to the power B I X I, which is computed by this rho is the density matrix, probability density matrix. So, this we need that that e to the power minus X transpose A X, that complicated looking stuff. Remember, that was the density matrix. So, this is a n dimensional integral for different xi's. So, there are n xi's, n xi's, x1, x2, x3, xn, and I want of course to get this correlation x1, x2, x3 like that. Okay. So, I just write this as a, I mean this part is substituted here, exponential I expanded. Okay. So, there are infinite series, this infinite series part, that, so this m going to from 0 to infinity. I just substitute it here, okay, no problem. Now, this part is this expectation value of x I, x1 like that. Okay. So, ZB has lot of information. Now, so ZB, okay. So, here how do I get this quantity xi1 dot xim. So, we have ZB, which is this quantity with the source term. So, I think I should write ZB. ZB was exponential integral dnx minus xi aij xj, okay, plus bi xi. Okay. So, I want this xi1 like that. So, ZB is I have it here. So, actually you should focus on this one. So, I want, okay, but this is infinite sum right now. I had to pull out this one. So, as I said, I take this ZB, in fact you can look at it here. I take the derivatives, partial with bi1, partial with bim. I have m of them. I just take the derivative of this. So, each time my xi1, xi2, xi3 will come out and will sit here, xi1, xi2, xim. Okay. So, that is what we would like, and that is what I have it here, and we set b equal to 0. So, then I will get the expectation value of x. Okay. Now, I need to connect it to the 2-point correlation, product of 2-point correlations. That is a trick, I mean that's a complicated part. So, this ZB, I said it is this, right, this integral we should said is this. Well, by the way, I need to divide this by integral exponential minus xi aij xj. Okay. So, but this part does not do anything to the derivative. So, this part is that the integral of this is that we discussed so much, right. I mean half bi a inverse ij bj, and you set b to 0. After taking the derivative, you set b equal to 0. Everybody is with me. It's a bit complicated maths, but I said if you want the correlation, then you take the partial derivative with b's, source terms, and then set b to 0. Okay, and this has the answer. Now, of course, we need to do it carefully and pull out the 2-point correlations, and that is here. Okay. So, this part is this is not difficult, but just you have to follow my set of arguments. We call this as x. capital X. Okay. By the way, this is the only function of B's and A inverse and B. A is a matrix, A inverse is a matrix. Okay. So, I need to take derivative is with that. So, first I1 derivative, I take a derivative of X with this one. So, what will I get? So, this is A inverse. So, A inverse, so we have Bi and Bj. So, I am doing with I, well, I should part, so Bi1, so this, if I take the derivative with Bi1, so Bi1 will go away, no. So, B is a variable, if I take the derivative that will give you 1. So, I get Bi1 k Bk, because Bi1 in this, in that expansion will go away, and of course, the exponential will come here as well, but when I take the derivative I get A inverse I1 k Bk, and this I1 is sitting here. So, this is a number and I multiply by x. Okay. This is basically sum, right. For this there are n terms in fact in this. Is n by n matrix, I multiply by Bk and I get this. Okay, first part is done. I done only one of them. So, now let us take the other derivatives. Okay. Now, I just rewrote this part here. Now, take the other derivatives. So, this is the product, no, this one, and x has a Bk sitting there inside. This x is the exponential part. Okay. So, the B sitting inside x and the B sitting here. Okay. That is how I am going to get lot of terms. So, this one will involve. So, let us do with I2. If I do with I2, I am going to get A inverse I1 I2. So, K will, so in this sum I put K equal to I2, then the B I2 will be there, that will get cancelled and I will get A inverse Bk into x. Now, okay, right now let us keep non-diagonal. Okay, I think it is possible, but no, you are not, you have no diagonals. It is a independent variables x, y. So, example I give x, y, z, w, they are independent variables. Okay. So, product of two different variables, same is not allowed, same is not allowed. So, they are all different. So, when k equal to I2, I will get this, and now set b equal to 0. So, x at b equal to 0 is 1. Okay. So, this is the first term. Well, I am sorry, wait. I am not setting x equal to 0 because I need to take the other derivatives. Don't do it right now. I have taken the I2 derivative and I will get A inverse this one, and then this guy will act on x. Okay. But there is one more term which is set to 0. So, here I acted this one here and x was outside. Well, I mean, I think this is slightly complicated, my head is also spinning. A inverse Ij Bk multiplied by x, I do Bi2. So, Bi2 acts on this. So, this is A inverse Ij Bk, and Bk is gone and x will be there, plus then Bi2 x will come, and then A inverse Bk will come. Okay. So, when I take the b going to 0, this will go away. Okay. So, basically I get this one and the derivative will act on x. So, this product, some terms go away, and first time when I do I2, I get this one, and the remaining m minus 2 ones will act on x. Next operation we do with Bi3, I get A inverse I1 I3, and then these guys will act on x. So, I basically I reach line 3, I have done two derivatives operations. and you can see that we get all the 2-point correlations are coming out, I1, I2, I1, I3, I1, IM. Now we have m minus 1 derivatives to be computed for other objects. So we follow the same thing recursively. Okay, so you just follow the same steps, and we keep taking b going to 0 limit where we don't need to do derivatives anymore. For example, I was saying here that this guy is going away. Okay, and and then you just follow this da 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 da. Okay, then we will get all the products. So this is a recursive proof that if you do it all these derivatives, then I will get all possible products of 2-point correlations, and is written as sum of all pairs A inverse I P1 P2 P3 P4 Pm minus 1 Pm. Okay, so it's a pretty complicated, well, it's a bit tedious, but if you follow the idea, you will understand the proof. Okay, m derivatives, but then you do 2 of them, then remaining m minus 2, then keep doing it. This for odd even ones, huh? Odd one is 0. Okay, so we will use this in future work, but this is Wicks theorem for statistical field theory, and quantum field theory we will start in the next class.